As a user of Autodesk Inventor, you often become focused on one aspect of the program as you work. Most projects only use a small portion of Inventor's toolset, like modeling, creating assemblies, and creating drawings, which, granted, is a major portion of what most Autodesk Inventor users do on a regular basis. But sometimes it can be useful to see other aspects of a program every now and again. Recently, I was developing a presentation and lessons for one of my CAD learning courses in Autodesk Inventor. So for this video, I decided to take a few minutes and get outside of my normal Inventor bubble. Hi, I'm Stephen Shane, aka the 3D Professor, and this is the 3D Professor's Lab. In this video, I'm not going to walk through one particular workflow for a project. I'm going to cover some Autodesk Inventor features that I normally don't work with on a regular basis anymore. I'll look at some cable and harness features for placing electrical components, routing wires, and setting up nailboard drawings. Then I'll get into a little bit of sheet metal, focusing on standards and creating sheet metal rules. We'll cover a little bit about weldments and creating welds, then configuring punch tools, and creating an iFeature that you can use to punch into sheet metal. We'll wrap up with creating a table-driven iFeature that can be used to punch into sheet metal as well. And don't forget to punch that like and subscribe button too. Well, without further ado, let's get on with it. Starting with cable and harness, electrical parts like connectors are standard Autodesk Inventor parts, or they're iParts, with one or more pins and extended properties assigned. You can add pins individually or as a group. You can use generic connectors from the Content Center, or you can author and publish your own. You can also place any non-library connector in the assembly using the Place Component command. The connectors in this assembly file are standard Inventor parts that can be downloaded from either the Autodesk Manufacturing Supplier Content Center or a place like Trace Parts or any other online repository. I'll go ahead and open the first assembly, and I'm going to add pins and prepare the yellow connector for use in a harness assembly. I'll select the yellow connector on the bottom, right-click on it, and select Edit. Now, I could open this part, but it's just as easy to edit in place. On the ribbon, 3D Model tab, Harness panel, I'll click Place Pin. When I hover the cursor over the part geometry, notice the valid points highlight. I'll hover over the top edge of the red face cutout, and a green center point appears. When I click on the edge, a pinpoint is added to the geometry. In the pin dialog box, I'll use the default name of 1. When I click the green check mark, a work point is placed representing pin 1. I'll repeat the process and create pins 2 through 9, working from left to right, with the green faces pins 4 and 7, with pin 4 being the middle one. You don't have to click the green check either. Simply pressing Enter accepts the default name. The default pin name is a sequential number starting with 1. If the existing pin names are not sequential, the default pin name increments from the lowest unused value. I'll right-click and select Done to exit the Place Pin command. Then I need to add a reference designator placeholder. It's an identifier that maps the part to a schematic design. You generally add a placeholder such as U question mark. The question mark represents the associated occurrence in the assembly and is replaced by a number. For example, U1, U2, U3 would add a unique identifier for each instance of that connector. So with nothing selected, I'll click on the harness properties. In the part properties dialog general tab, I'll enter a reference designator of U question mark in the ref des field, then close the dialog. I'll go ahead and switch over and open Assembly 7, and we're going to look at routing wires. Once the pins are in place, you can begin placing wires and harnesses. After the wires are placed in the harness assembly file, you can create segments, then route the wires through them. In this assembly, segments have already been added, but a few wires still need to be routed. I have the option of routing them manually or automatically. I'll right-click the harness assembly and edit it. With manual routing, on the ribbon, Cable and Harness tab, Route panel, I'll click Route. First, I'll select the wires that are going to be routed. In this case, I'm going to pick the 2 wires that go to the power supply board from the yellow connector on the bottom of the box. I'll click on the first segment, then select the blue segment coming out of the yellow connector. Click Last Segment and select the segment going to the power supply, and then click Apply. That routes those 2 wires through those 2 segments. Once I've applied the first route, I can start over or try automatically routing the wires. Automatic routing looks to see what segments are closest to the beginning and ending of the wires. The option for all unrouted wires can be used to route any wires that have not already been routed. Keep in mind though, this may route wires in ways you don't really want them to be routed. In this case, I know that choosing all unrouted wires works, so I'll check the all unrouted wires checkbox and click OK. So that gives you an idea of some simple operations in Cable and Harness for creating wire harnesses. And once wires have been routed, I can make changes to the routes by editing the assembly, then opening the segments and moving the points that make up each route. Right-clicking on the point and picking 3D Move and Rotate lets me modify the position of the point. I can move the point and accept the new location, and the harness updates. So authoring electrical components can be done once you have wires routed. It doesn't matter at what point you want to do it. You can author electrical components to a custom library. Once you have libraries set up in your project that are read-write, you can use the Manage tab to publish a part to a custom library. To publish the yellow connector, I can edit it in this assembly, then click over to the Manage tab, Author panel, and from the Author dropdown, pick Connector. The Connector authoring dialog box opens, and since this part was already configured as a connector, the authoring tool pulls the information from that part. All I have to do is click OK. If everything goes well, I'll get an authoring successful dialog box that pops up, and I can click OK to close that and move on. From this point, Inventor lets me create a nailboard drawing for the harness. I'll start by opening a base drawing, wireharness1.idw. From the Place Views tab, I'll create a nailboard view. In the nailboard view assembly dialog, I'll open up the Chapter 5 Assembly 01.iam file. Once that loads, I can pick Wire Harness 1 from the nailboard view dropdown. I'll leave the view scale and view identifier alone. There are some display options you can modify, but I'll leave those alone as well, and click OK. This will place the nailboard view in a sketch. I'll finish the sketch and add connector views. On the nailboard tab, if you want, you can place connector views. This will automatically pull connectors attached to the ends of the wire harness. Once I've added the connector views, I'll add harness dimensions using the intersection point as the reference. I'll add a dimension on the left side, the right side, and the vertical segment. Let's move on to sheet metal. I'll go ahead and open the junction box sheet metal part. When working with sheet metal, you may want to define specific rules that govern how sheet metal works for different materials and material thicknesses within your process. For example, if you're using aluminum versus steel for bending sheet metal, and if you're bending a thin material like 030 or a thicker material like 1/8 inch or 1/4 inch. When you're in the sheet metal workspace, you can click to define the sheet metal defaults. And from there, you can define various rules for the materials you're working with. By opening the Style and Standards editor, you can edit sheet metal rules. Clicking New, I'll add a sheet metal rule and name it 16G, 16 gauge stainless. I'll choose the stainless steel as the material and set the thickness to 0.063 inches. Switching over to the Bend tab, I'll set the relief shape to round. Then jump over to the Corner tab and set the relief shape to round there as well. Then I'll save the sheet metal rule. Now I can also add a table that specifies the thickness and bend radius for the unfold rule. Clicking Import, I'll set the option to Sheet Metal Bend Table, navigate to the Workspace folder, and click on the Bend Table 1 inch text file. Once that opens, I can view the results of the import, and I can see there's now a table for 2 material thicknesses. I'll go ahead and click Close and Save, and close the Style Editor. Back in the sheet metal defaults, I'll make sure the 16G stainless sheet metal rule is selected and choose Use Thickness from Rule, and click OK to close the dialog. Weldments are another aspect of Autodesk Inventor that are easy to create, but very powerful to use. And creating a weldment is a fairly straightforward process. The caveat is that once you create a weldment, you cannot go back to a standard assembly. The difference between a standard assembly and a weldment is that all the parts in a weldment are considered one piece and will show up as one weldment on a bill of materials. In the Environment tab, you can convert an assembly to a weldment. Once you convert a weldment, you can specify the weld standard along with the material and bill of materials structure. Clicking OK accepts the weldment configuration, and you're ready to move on to creating welds. Now, once the assembly is converted, you can begin adding welds. The Weld tab has a number of options for dealing with welds. You can prepare a surface for a weld and add a weld, as well as configure machining for welds. There's also a weld calculator you can use to check weld loads for different types of welds. Adding the weld, like a fillet weld, is performed by clicking the weld options in the process panel. Here, I'll click Groove and add a groove weld to one of the seams. I'll turn on chain faces to make it a little bit easier. For the bead, I'll select the face 1 set, starting with the inside of the corner, and work my way down one side of the bend. Once I get to the bottom, I'll click on face set 2, start with the inside of the top corner, and again, work my way down, selecting the faces that will be in the second set. For both set 1 and set 2, I'll turn on full face weld. There's also an option to set a radial fill as opposed to a flat fill. And I can automatically create the weld symbol at the time I create the weld. Clicking OK creates the weld and adds it to the weldment. When I'm done adding welds, I can return to the top level weldment. I'll move on to configuring the punch tool catalog. When working with sheet metal, you often use punches as tools, right? Those punches are stored in a catalog and can be stored either locally or in a shared folder on the network. To set the location of the sheet metal punches root folder, on the ribbon, Tools tab, Options panel, select Application Options. The Application Option dialog opens. Select the iFeature tab. You can see here that the sheet metal punches root is currently set to the catalog on my local computer, and any punch feature I make should be stored in that folder. I'll go ahead and close the application options, and I'll move on to creating a punch iFeature. This is a simple face created from a rectangle with a sketch extruded through it to cut the material away. This is the beginning of a punch tool iFeature. To create a punch tool from this, I'll switch over to the Manage tab. I'll open the Parameters dialog so you can see what parameters are set up for this punch tool. You can see the sheet metal parameters that include the thickness, bend radius, and so forth, plus the model parameters that include the cutout width, cutout height, hole spacing, and hole diameter. I designed the sketch to always work around a center point, no matter what size the model parameters are. I'll go ahead and close the Parameters dialog, and in the Author tab, I'll click Extract iFeature. For the type, I'll switch to Sheet Metal Punch iFeature. Then pick the extrusion that contains the cutout sketch. This brings in all the parameters associated with the sketch in the feature, but only brings in the named parameters in the Size Parameters window. For the simplified representation, I'll click to select the sketch and check the option to unfold in flat pattern. In the manufacturing specified punch ID, I'll type 300A as the ID. Clicking Save opens the Save As dialog. I can double-click on the punches folder to open it. I'll select the 300A switch cutout IDE file and just save over that. If you get a warning about the location is not in the active project, don't worry. Since this is a punch tool folder, you don't really need this in the project, but you can add the folder if you want at another time. I'll click Yes, save the file, and I've created a new punch. Creating a sheet metal component requires a sketch that locates where the punches will be made. The punches in the current catalog all start with a center point. This sheet metal box has a sketch that places 2 points on the back side of the box. Opening the Sheet Metal tab, Modify panel, I'll click on the Punch tool. In the Punch tool directory, I'll click on the 300A switch cutout and click Open. This opens the location into the Punch tool dialog and selects the 300A cutout. However, here I can select any of the other punch tools if I want. There are a couple of options. If this is going to be across a bend, I can have it allowed across a bend. I can also have it unfold in the flat pattern, which I'll make sure is checked. And then the flat pattern punch representation I'll leave at default. There are a few options for how the punch is represented, but the default always works for me. I'll leave the geometry alone and we'll flip over to the Size tab. Here I can change the size of the cutout, and this will affect both cutouts. If I want to make these punches for a different switch, I can do that here. Clicking Finish adds those punches into the geometry. Clicking on the flat pattern shows me those punches in the flat pattern. Once the punch tool is created, you may want to customize it for multiple size options. I'll open the switch punch cutout.ide file, and now I'm presented with the iFeature tab. To create a table-driven iFeature, I'll click on the iFeature Author Table option. The first thing I'll do is remove the punch tool depth parameter by right-clicking on the option in the Parameters list and selecting Delete Column. I'll switch over to the Manufacturing tab and remove the Punch ID column in the Alt Rep column, again by right-clicking and selecting Remove Column. Jumping over to the Properties tab, I'll open the Project folder and add a description column by selecting it and clicking the Add Column button in the middle. I'll make a few changes to row 1, setting the thickness value to thickness, then adding a description. I'll type in 300A space M1 space SP. This will be for a single pole switch. Then I'll right-click on row 1 and insert a new row. I'll change the cutout height to 0.463 inches and change the description to read 300A M1 DP for the double pole switch. I also made a mistake when entering the original cutout width. It should be 0.517, not 0.57. So I'll make that change in both row 1 and row 2. When I'm done, I'll click OK to save the iFeature table. When I open the iFeature in the browser, I see the table. And when I open the table, I see the two cutout options. I'll go ahead and save the file as a new file name. I'll name it switch punch cutout 02.ide and click Save. Going back to the sheet metal box, I'll go ahead and use the table-driven part as a punch tool. This works exactly the same way as any other punch tool works. However, the difference is you now have options for selecting the size. So I'll go ahead and get rid of the old punch, and I'll keep the sketch. Then I'll click on the punch tool, navigate to the workspace, components folder, and open switch punch cutout 02.ide. I didn't put this in the library, but it doesn't really need to be there for this demonstration. The same thing happens. I have the tool punch dialog. I can click the unfold in flat pattern option, but now I have a punch tab. In the punch tab, I can click on the description and choose the 300A M1 DP option. Notice that changes the cutout H value. And when I click refresh, the cutout size updates for the pattern. When I click finish, the punch pattern updates. And that's using table-driven iFeatures as a sheet metal punch. I hope you enjoyed this video overview of Autodesk Inventor cable and harness and sheet metal topics. If you like videos like this, leave a comment below and let me know what topics you'd be interested in. Don't forget to please like this video and subscribe to my channel. Until next time, I'm Stephen Shane, the 3D Professor. It's time to go home.